Now that we've laid the foundation for Lenz's law, we're going to look at some different type of examples that you can encounter on an exam. So we'll try to show you every possible situation that's going on. So we're being asked in this question to sketch the directions of the induced magnetic field and the induced current. So before we do that, let's have a look at what's going on. What I have here is I have a bar magnet. It's falling towards this, maybe it's a copper pipe or some other ferromagnetic material. Now what I notice here is I have the north end of this bar magnet approaching this end of the pipe here. Now we have to think back to Lenz's law very carefully. Lenz's law states that the system is always going to try and oppose the change. So whenever we have a magnet coming towards an object, the object has to generate a magnetic field to try and slow that down or to try and oppose what it's doing. Now, in order to do that, if this is coming closer, we don't want this to get closer. We want to try and stop that. The best way for that is if this end of the tube acted like a north pole, and then the base of this tube here, this acted like a south pole. What that's going to do is that's going to cause a little bit of repulsion here. There's going to be that magnetic force of repulsion between this ferromagnetic object and this falling magnet. So with that, first thing we can do is we can sketch the induced magnetic field. We can almost think of this kind of like a solenoid without the wire, but we have a north pole here, we have a south pole here. So to sketch the magnetic field lines, we're going to start on the north pole, kind of go around to south pole. We're going to leave the north pole, enter the south. We'll kind of just repeat that on the other side here. And then we could have the field lines going through here too. So that's going to be our induced magnetic field that's generated. So this magnetic field's job is to oppose that falling magnet there. Now we've also been asked to sketch the induced current. We're kind of doing it a little bit backwards in the sense of what's happening. What's actually happening is that when this magnet falls, the induced current is generated such as to produce this magnetic field. What we're doing is we're just sketching the magnetic field first to get the induced current. Nothing wrong with that. Now, this is going to be an application of our second left-hand rule. Now, what we have here is we have our configuration with the field lines. It's pointing up through this tube, and we have the magnetic field lines going around. So we have the north end at the top of this pipe. What we want to do is we want to pretend that we're going to grab this pipe with our left hand because we're dealing with current, and current is electron flow in Alberta. What we want to do is we want to grab this tube with our left hand. We want the thumb pointing towards the top, and we want the thumb pointing towards the north pole. So what you're going to notice is that if your fingers wrap around this tube, your fingers are going to wrap around such that your fingers are going from the right side and pointing to the left side. So what's going to happen here is your current is going to go around the tube such like this. So that's my induced current, and that's my magnetic field strength. Or if you want to draw it the other way that we could certainly look at that too is on the right side, it's coming towards us, so we could mark that with an X. And then on the left side, it's sort of going into the page, so we could mark that with a dot. That also works too. But the main thing is that the current, if we're looking at the tube straight on, it's coming from the it's coming from the right and moving towards the left. So when this magnet falls, this is the induced current that is generated in order to produce this induced magnetic field to oppose the motion of this magnet. So we're going to look at a couple more examples with this. So this time we don't have the object trying to move towards this ferromagnetic material. It's actually trying to move away. So this time what we're told is we're told that the north pole of the magnet, it's being pulled away from a copper ring. So we want to find the direction of the induced current in the ring. Again, it all comes down to Lenz's law disliking change, or systems disliking change. It's always going to try and oppose. So if you have a magnet coming towards the object is going to try and oppose that and slow the magnet down. If you have a magnet moving away from an object, the object doesn't want it to move away. It's going to oppose that, so it's going to try and pull that a little bit closer. And I'll give you a really poor analogy on that later. So this North Pole, this is trying to move away. This ring is not going to like that. This ring wants to pull this back closer. Now I'm going to just sketch the ring here. I'm just going to sketch more of like a side view of it. So kind of here's my ring. Here's my bar magnet moving away. Now if that North Pole is moving away, this ring isn't going to like that. If this is trying to get away, the ring is going to pull this back. The only way it's going to be able to do that is if we have a South Pole on this right side of the ring, and then we have a North Pole on this south side. Because then this will generate a magnetic field. This will generate an induced current to produce a magnetic field that's going to try and attract that North Pole back to oppose its motion of going away. It's a little harder to visualize with this one. It's still an application of the second hand rule. We're going to have our thumb pointing towards this North Pole, so we're going to pretend we're grabbing onto this ring. And again, you're going to have to imagine it, but you have to put your thumb towards the left, and you have to grab around that ring, and what you're going to find is you're going to find that the current comes down the ring in the front like this. So that's my induced current. Now let me just blow up that sketch a little bit because it's really crammed there. But again, if this is sort of my ring here, and I apologize, my 3D shape drawing is really terrible. So what we had here is we had the north and south poles of our induced magnetic field, and then the induced current that will produce that. It's going to come down here in front of the ring. One of the hard parts of Lenz's law is the whole visualization aspect. On an exam, you're not generally going to have wires and copper pipes, and well, most of you probably won't have rings. So you're going to have to get really creative and really imaginative with this. Right, the last one, very similar idea. We're going to have galvanometers this time. So we have a bar magnet. It's moved relative to a coil as depicted in our diagrams below. So we just wanted to determine the direction of the electron flow through the galvanometer in each situation. So again, when we're talking about electron flow, we're talking about current. Now again, think of Lenz's law, always do the opposite, or we always want to oppose motion. So if I have this south pole approaching, this galvanometer, this system is saying, nope, you are not getting any closer. So in order to do that, what's going to happen is we're going to have a south pole at this end, and we're going to have a north pole at this end. So that is the induced magnetic field that is going to stop this magnet, or going to attempt to stop this magnet from getting closer. What we need to do now is we need to figure out the direction of the current. Again, we're really getting good with our second hand rule here. We want our thumb pointing towards this north end, and then if we try to grasp onto this wire, or this coiled wire, we're going to find that our current, it's going to come down the wire here. So this is our electron flow, and then we're going to trace that through the wire. And what we're going to find is as it passes through the galvanometer, the current flow is going to go right through the galvanometer. And again, I apologize for my poor writing. Now, instead of this south pole trying to approach this magnet or this coil of wire, now we have this north pole, but it's trying to get away. Now the system's upset. It's kind of saying, no, don't go away, come on back. So we have this north pole trying to get away. Well, for this system to try and bring that back, what we have to do here is we have to produce a south pole here, and then we'll have our north pole on this end. Because what's going to happen now is that induced magnetic field is going to attract this bar magnet and try and bring it back. It's going to oppose that change. Now this is exactly the same configuration we just have. So if we do our second left hand rule with the thumb pointing towards the north, we're going to find that our electron flow is going to come down through the wire. It's going to go through the galvanometer, and it's also going to go once again right through the galvanometer. My analogy to Lenz's law is this, and it may not be the best analogy, but it's the best one I could think of in the time being. I always like to think of Lenz's law as kind of like two people getting to know each other on a date. When one person tries to get a little bit close, there's sort of that rejection, kind of like, get away from me. Same thing with Lenz's law. If you have a magnet approaching a system of some kind, that system is going to try and oppose that and say, nope, get away. Well, same thing with two people kind of getting to know each other. If one decides, well, I don't want to be a part of this, I'm getting out of this, and starts to walk away, the other person's going to be like, no, come back, I'm sorry. Same thing with Lenz's law again. The magnet tries to get away from the system's like, oh, no, I'm sorry, come on back. So the main thing we want to take with Lenz's law, if a magnet is approaching a system, the system is going to generate a magnetic field to oppose that motion, to try and get it to prevent it from coming closer. Whereas if the magnet is trying to move away, the system will generate an induced magnetic field in order to try and bring it closer. Lenz's law is always about doing the thing to oppose the system. Sorry, let me rephrase it. That was poorly phrased. Lenz's law is all about opposition. The system will always oppose any change. And this can be summed up in just a few words. Nature hates change.